Alright, how's it going pre-AP kiddos? Last distance learning video of the spring here. If you're watching this, make sure you come check in with me next year just to wave and say hi. But this is equilibrium. This is going to be a short little intro to equilibrium. If you're taking AP with me, we spend 6 weeks on equilibrium next year. At least in theory if we ever go back to school. So here we go. So you can take little notes on this. There's a worksheet attached to this that I think is really healthy to do, especially if you're just killing time this week. So here we go. Chemical equilibrium is a dynamic condition where the rate of the forward reaction is equivalent to the rate of the reverse reaction. So reactants are turning into products at the same rate as products are turning into reactants. So it ends up in this spot looking as if nothing's going on because the amount of reactants and the amount of products stay the same. But it's a dynamic condition in the fact that these guys are moving that way at the same rate these guys are moving that way, and so the reactant and product quantities are the same. It's I use a swimming pool analogy of when the swimming pool opens at 8 in the morning during the summer, it's just old people going to the swimming pool. So you got a bunch of old people in the swimming pool, and then come 10:30 or 11, the young people start to arrive. And what happens as the young people start to go into the swimming pool is that those old people are like, oh no, kids. And so those old people start to get out of the pool. And so the side of the pool and the number of people in the pool doesn't change as far as numbers of them. If there are 5 kids that are showing up and there are 5 old people, well, let's call it 7 old people. There's 7 old people sitting in the swimming pool. Then if a kid gets in, an old person gets out. So there's still 7 people in the pool and there's still 5 people on the side, but it is a dynamic condition where they're changing at the same rate. So every time somebody comes in, somebody comes out, and the quantity of people in and out of the pool stay the same. That's what equilibrium is. These two values don't have to be equal. It doesn't have to be 5 people out of the pool and 5 people in the pool. It just has to be that the concentration of each of these is no longer changing, right? As the reactants go to products, the products go to the reactants. That's the idea with equilibrium. So it gives us a picture of this. It's just an okay picture of this. It comes from your textbook. But it gives us a reaction of A and B and C and D. We know that this dotted line here has to be A and B. How do I know that this is A and B? I know that's A and B because there's some of it there, right? There is an initial amount of those reactants in the products at the beginning. We got none of the C and D as this thing goes on. And what happens is as A and B turn into C and D, then we start to get a bigger and bigger concentration of C and D. This is not equilibrium because the concentrations of those things are changing. What happens is as A and B turn into C and D start to turn back into A and B. And at this point here, you see the reaction rate has flattened out, is not changing anymore. This implies that the number of products and reactants are equivalent, which is not real pretty because I don't even know a reaction that does that. It could just as easily have lines that look like this, where C and D flatten out here and A and B flatten out here. If this is A and B and this is C and D, the reactants and products, this is no longer changing its concentration, right? The rate has flattened out. In this case, A and B, there's a higher quantity of them or higher concentration of them at equilibrium than there is C and D. But it's still equilibrium because as C and D are changing to A and B are changing to C and D at the same rate. So that works. So I'm going to give you a couple little quick little hitter problems. This is called an equilibrium expression. It's given and I don't even know if the letter shows up there, it's K is the equilibrium constant. So it's a capital K, and that capital K is the equilibrium constant. It's a ratio of concentrations of products over their reactants raised to their coefficients is how you solve for this equilibrium constant. So here we have a reaction of hydrogen gas reacting with iodine gas to form 2 of those hydroiodic acids. So our K value would be products That's the HI raised to its coefficient. So HI is concentration squared, again brackets mean molarity, that is the concentration, over the top of, so products raise their coefficients over the top of, the reactants raise their coefficients. Now no coefficients here, so it's the concentration of hydrogen times the concentration of iodine. I'm going to give you a chance to set one up on the next slide, but that's how we write an equilibrium expression. On a side note, and this will matter for you next year in the second year course, the only thing that goes into equilibrium expressions are aqueous things and gaseous things. No solids or liquids. So if anything in here is a solid or a liquid, it's not part of the equilibrium expression. And the reason that is because solids and liquids, their concentrations are so high that we don't see a change in those concentrations, and therefore they're not included in the equilibrium expression. So here we go. They give us an equation. It says calculate the equilibrium constant. They give us values for all of these guys. How do I do this without a calculator? So here's what it looks like. K would be equal to the concentration of products. So we have F. Its coefficient is 1, so it's raised to the first power. We don't have to write the 1. Times G cubed. Those are our products, divided by our reactants, which would be D raised to the first times E squared. Perfect. So our calculated equilibrium constant would be equal to, and same thing we've done all year, generic equation with the numbers in it. F is 1.8 times G is 1.2 cubed, all divided by D is 1.5 times E is 2.0 squared. And we would plug those guys into our calculator. I'll glance and see if I got a calculator handy. We plug those guys in the calculator, and that would tell us what our equilibrium constant is. Equilibrium constants, you'll have to do it for me. I'll put in, and maybe I'll put in the first comment what the K value is here. But equilibrium constants are one thing that we have that doesn't have a unit on it. So there's no unit on that value. That value, ready? If K is greater than 1, that means products are favored. That means in this reaction, we would have a higher concentration of F and G than we would have of E and D. The reaction would be favored towards the product side. If K is less than 1, then reactants are favored. That's how we describe that. Fair enough? Fair enough. I think there's one little slide left, and this one little slide, it's the same equation here. Is the first problem we looked at, and this is talking about shifting equilibrium. And so I'm just going to talk real quick about a couple shifts in equilibrium just so you can get your head around it a little bit. If we change the pressure, right, that's the same. So if we increase pressure, that's decreasing volume. Yes, when you look at those, in pressure's case, a greater pressure, increasing the pressure, means we shift to less moles of gas. If we increase the pressure, that's shrinking the volume down, right? And so if we push gas particles closer to each other, they run into each other more often, and they will condense more often because their intermolecular forces are forced to take effect. So increase in pressure means shift to less moles of gas. That means a decrease in pressure would cause us to shift the equation towards more moles of gas. Now, when we look at this equation, it's irrelevant here because here's 1 mole of hydrogen and here's 1 mole of iodine, where coefficients represent moles. So we have 2 moles of gas on the reactant side We have 2 moles of gas on the product side, which means the pressure changing here is not going to affect our equilibrium, or at least it's a negligible amount, because we have equal numbers of moles of gas on reactant and product side. For the other ones, for temperature and concentration, the general shift is a result of if you increase something on one side of the equation, it tends to cause the reaction to shift across the equation. So, and we talked a little bit about this in solutions. But if I look at the temperature here and I increase the temperature, that's increasing the kinetic energy of the heat energy. And so when we look here, that's 78 kilojoules. When we increase something on the right side of the equation, that equilibrium will shift across the arrow. So if we increase temperature here in this exothermic reaction, that would cause us to shift towards reactants. If we decrease something on one side of the equation, it causes it to shift to the same side. So if I decrease the temperature, then that would cause a shift towards products. And we'll talk about the reasons for that next year in AP. And then concentrations work the same way as the temperature. If we increase the concentration of hydrogen, it shifts across the arrow. So increasing the concentration of a reactant would cause more products to form. If we decrease the concentration of a reactant, so we decrease iodide, it would cause the reactants to shift to the same side. So that would cause more hydrogen and iodine to be formed. So increasing something on one side, shift across the arrow. Decreasing something on one side, shift to the same side of the arrow. And then you've got your little tricky ones with pressure. And there's other shifts in equilibrium that, as we get into more detail, we'll look at. So I encourage you go look at that. It's a workbook page that I'm putting up there for you on Google Classroom. Take a peek at it, play with it a little bit. Don't get overwhelmed by any means on it. And if you got questions on that, I'd love to hear from you. So take care. If I don't see you, have a great summer, and check in with me if I can do anything for you. Talk to you soon, hopefully. Bye.